So the GST scheme is a scheme that chooses in between these two. So we know that adding a dissipative flux proportional to delta x cubed times the third order derivative of u is appropriate for smooth regions of the solution. And adding what we added before, a dissipation proportional to the second order derivative, a much stronger dissipation because it's proportional to delta x instead of the much smaller delta x cubed, is appropriate around shock waves and the local extremas. So the GST scheme is simply a scheme that chooses in between them according to the same limiter we have been using to reconstruct the solution. So the first step is to construct a limiter phi that is equal to 0 or 1 for if 0 is non-smooth and 1 is smooth, and they can also go in between. So we can use the same limiter we used in our scalar conservation law. And second step is to construct a second order derivative. So second order dissipation flux, which is proportional to the first order derivative times the maximum value of the characteristic speed. And third step is to construct a numerical dissipation proportional to the third order derivative that is going to give us a fourth order dissipation. And then combine them using the value of phi in such a way that if phi is equal to 1, then we are purely using the third order derivative, and if phi is equal to 0, we are also going to be using the first order derivative. All right, so for example, we can multiply, we can have this value, the third order derivative, to be also always times 1, and the second order derivative to be times 1 minus phi. And that gives us the appropriate behavior of when phi is equal to 0, we turn on the stronger dissipation, and when phi is equal to 1, we turn off that stronger dissipation. So that's how the GST scheme deals with system of conservation laws, achieving second order accuracy but still being non-oscillatory around shock waves. It computes the limiter the same as what we compute before, based on local extremas and the ratio between slopes between different solutions. And I'll construct a second order and fourth order dissipation and perform linear combination of them, turning the second order on and off according to the value of the limiter. So this is the most advanced material we are going to go into in finite volume schemes. So with this also applies for multiple dimensions. The only difference in multiple dimensions is that the gradient reconstruction. So here we are constructing the gradient by just taking the difference between two adjacent cells. In multiple dimensions, you need to take more than 2 cells to reconstruct a gradient. Usually you take multiple cells around you and perform a least squares type of estimate for the gradient value. Because in 2D, for example, the gradient gives you 2 values, right? So in X and in Y. But like the number of surrounding cells may be more than 2. So you have more equations to satisfy than unknowns when you're trying to calculate the gradient. If you have exactly 2 adjacent cells, like in a, then you can solve 2 equations for 2 unknowns being the gradient. If you have many cells around you, you have an overdetermined system and you use these squares to get the gradient. But other stuff are the same, okay, in multiple dimensions. Yes?
I'm not very clear how to use the limiter to decide how to include the third order dissipation.
Oh, that's a good question. The third order dissipation can be always 1. That's the simplest way to determine the third order dissipation. Right? It's always on, because if we don't have a shock wave, it can be there, providing stability while giving us at least a second order accuracy. When you are around the shock wave, it's also okay to have this term in, because the second order proportional to delta x term is going to be overwhelmingly strong. So you don't have to diminish the third order term when you're around the shock wave.